All right, so the question now is to relate the entropy defined in this particular case on the statistical basis with thermodynamic macroscopic things like heat and so on. So we consider an open system at equilibrium with its surroundings, and that's equilibrium. So here we have a system. The system has a certain internal energy, it has a certain volume, and it has a certain number of moles of A, number of moles of B, number of moles of C in it. Okay, and the state of the system is, these are all extensive properties, and the state of the system is determined by these extensive properties. All right, so the system is now at equilibrium. It's at internal equilibrium, it's at equilibrium with the surroundings, and we make a slight change. We're going to change the volume of the system a little bit. Okay, we're going to change, oh, sorry. It has a certain entropy, it's a state property. And the state of a system is completely defined actually by its extensive properties. I haven't got any intensive properties here. Okay, if I define an entropy, a volume, a total number of moles A, B, and C, actually that's all I need. That's going to determine the internal energy of the system and everything else. Okay, so now it's an open system, so I'm going to change the volume by dV. I'm going to change the number of moles of each system by dNi. In other words, I can add or remove moles of things. And I'm going to change the entropy by ds somehow. And the state of the system will change, and there will be an accompanying change in the internal energy of the system. Okay, so the accompanying change in the internal energy of the system, du, will be equal to du ds at constant volume, and n means constant number of moles of everything, ds plus du dv plus sigma mu I dni, where mu I, okay, just calculus. Okay. So mu I is the chemical potential of component I, which will be discussed probably the day after tomorrow. So for the moment, if you want, you consider it to be a closed system. We're not changing the number of moles of Ni, but that'll come later. So we expect that the temperature, now the absolute temperature then is given as, or is defined as that. This is in the statistical version of thermodynamics. This is in fact the definition of temperature. It's the change of internal energy with entropy as you keep the volume and number of moles constant. So I keep the volume, the number of moles constant, I increase the entropy of a system at equilibrium a little bit, and the internal energy decreases by du, and du ds is equal to the temperature. Okay, du is, if I increase the entropy, I'm obviously going to increase the internal energy as well. Temperature is always a positive quantity. Now you see in this, I'll show you more what this means in a minute. I'm trying to do this here the proper way. In this case, actually, this is the definition of temperature. Temperature is defined in terms of the energy and the entropy. We consider the entropy to be a fundamental property of the system, and this is actually the temperature. In the classical version of thermodynamics, developed in the 19th century, it's the other way around. We think of temperature as an intuitive property, as being a potential, thermal potential for the transfer of heat. And then we would say, we turn this the other way, we would say that the change in entropy of a system is equal to du at constant volume number of moles over T. So the classical definition of entropy is this. The way we do it the other way around is we start with, so you start with temperature as being somehow intuitive and you define entropy. Here you think of entropy as somehow intuitive and you define temperature. Let's look into this a bit more. So we expect the temperature, however, we define, okay, we make this definition, but is this really temperature? Temperature should be defined so that heat flows spontaneously from high to low temperature. We want temperature to be a thermal potential. To show that this temperature defined this way is in fact a thermal potential, we consider two closed systems. So we consider two closed systems in thermal contact. So here we have system 1 and system 2. We'll isolate them from the surroundings, and they're in thermal contact. Let the temperature of the systems be T1 and T2. These are T1 and T2, where T1 is greater than T2, where T1 and T2 are defined this way. Suppose that heat flows from system 1 to system 2. So we have an energy flows this way. du flows that way. So this is du, so we have du2 equals minus du1, du2 then du2 is greater than 0. Heat flows from 1 to 2, let's say. So assuming heat flows from 1 to, energy flows from 1 to 2 in the form of heat, because there's no work. So the only way that energy is flowing is in terms of heat. This is a fixed boundary, nothing's moving. And by the first law, du2 is minus du1. Energy is conserved because it's insulated from the surroundings. So du2 is greater than 0. So let's calculate the total entropy for this process. Okay, I should be using always this. By the way, Jenny, if I use this cursor, then it shows up on your screen. Okay, so I should not be using the pointer. Okay, so let me know if I'm doing it wrong. Okay. So ds then is from this definition. ds1 is du1 over t1. ds2 is du2 over t2 from this definition. I've assumed, okay, du2 is minus du1. I've assumed that t1 is greater than t2. So if t1 is greater than t2 and the heat flows in this direction, the total entropy change will be greater than 0. So the heat flows in that direction. Okay, so that shows that T then, defined this way, is a thermal potential. Heat will always flow from high temperature to low temperature. That's why we define it this way. Okay, so we have a thermal potential. That is, the flow of heat from high to low temperature results in an increase in total entropy, and hence from the second law is spontaneous. The second term in equation 4 is clearly minus PdV. So this is the energy change. As you change the volume, the energy changes by minus PdV, the volume of expansion. Okay, so du dV at constant S and N is minus P. This term is minus PdV, right? It's the work term. Okay, this term is what it is, and this term then is TdS. Okay, so what we end up with is the first term is TdS, and TdS is then the reversible heat. Okay, so du is heat minus heat plus work. du is dq plus dw. This is the work term. Let's assume for the minute that's a closed system, so that term's 0. So this is dq. So du is dq plus dw. This is the work term of expansion. This is the heat term. And it's reversible, because I said the system's at equilibrium. We're making a slight change of the system at equilibrium. There's no irreversible process going on. Okay, so we come up with this equation, which is TdS is dq reversible. And that actually, in the classical version of thermodynamics, is where we start. We define ds as dq reversible over t, okay, saying that t is an intuitive property, and ds is dq reversible over t. In the modern way, we define t as du ds, but we've shown now that tds is dq reversible. And so this then makes the join, the join between the classical way and the statistical way, k log t, Boltzmann's equation in terms of energy states, and what we can measure in the laboratory, which is dq reversible. In other words, if we can keep temperature constant, for example, and measure the reversible heat of a reaction, we measure ds. So this relates the entropy to macroscopic things that can be measured. dq reversible then is equal to the change in TdS, and this is path independent since it's equal to the change of a state property. S is a state property, so ds is simply S final minus S initial. So this simply says that as you go reversibly from an initial state to a final state, if you take a system in an initial state and you go to a final state, if you take a system going from an initial state to a final state, and you do it reversibly. Now there are many reversible paths. There's not just one reversible path. There are several reversible paths. No matter which reversible path you take, the integral of dq reversible over t will be equal to S2 minus S1, which will be constant independent of all other details. So if you can keep the path reversible, and you take the integral of dq reversible over t, you've got the entropy change. Is that clear? TdS is ds is dq reversible over t. Delta S, which is S final minus S initial, is the integral of ds, integral of dq reversible over t. I'll give you a couple of examples of that. Putting all these things back into the initial equation, we end up with this, and this is called the fundamental equation of thermodynamics. Okay, if a system at equilibrium, if there's a change in entropy, ds, a change in volume, dv, a change in number of moles, dni, the change in internal energy is equal to that. That's called the fundamental equation of thermodynamics. If necessary to remember, it's combining the first and second laws. Assuming the only work term is the reversible work of expansion, in general, this will be the case. So, okay. If other types of work occur, because this is the PV, reversible PV work. If we have other kinds of work, then you have to expand the fundamental equation to add a reversible non-PV work term. The only time in this course, I'll talk briefly about it, where this is important, is we're talking about electrochemical cell, where this would be your reversible electrical work. If you're doing electrochemistry and you're measuring reaction Gibbs energies by a galvanic cell, or if you're running an electrochemical process like the Hall process for aluminum, you've got to add that term. Okay, so that doesn't really tell you anything. So we've done enthalpy, whatever. Okay, I'm going to stop right there then and give you a couple of examples. So from this equation, how are we going to calculate entropy? So ds is dq reversible over T. Oh, just to go back here then, I guess, as I said, I define T as, so here if you find T is in terms of Kelvin, Q is joules, so ds will have entropy has units of joules per Kelvin. Or since it's an extensive property, joules per mole Kelvin if it's a molar property. Okay, if you define T as equal to dq reverse, so T is du ds, a constant V and N, which is the same thing, then depends on the units of entropy. If entropy is bits, then temperature should have units of joules per bit. That's why we put the Boltzmann's constant, S is K Boltzmann log T, because we want to have it in, this converts your units to joules and so on, rather than going into bits. So actually, if you look at the, people talk about the fundamental units in physics. You have mass, you have length, you have time, and temperature is another one. But another way of doing it would be mass, length, time, and information in terms of bits. And then your temperature is defined in terms of information, not in terms of, okay, because really the temperature of the system has to do with potential for the flow of information. Okay, so how do we calculate the entropy change for a process? Using this example. Okay, let's take now the example then of your piston expanding. So here we have a gas at an internal pressure P, and there's an external pressure P external, or let's say P of the surroundings. P external is P of the surroundings, and P external is, say, less than P, so the thing expands spontaneously. And let's say it expands from T, let's say T is constant, and we'll have the thing expanding from V1 to V2. So it goes from V1 to V2, expand the same pressure. Okay, expanding from P1 to V1 to V2 at a constant temperature. All right, now we already did this before. What is delta S? Okay, so suppose it's kind of messy. Can I rub that out? All right. Okay, we have a gas expanding from P1 and V1 to P2 and V2 against an external pressure, P external, which is less than P, and T is constant. Okay, so here's your gas, P external, or surroundings, P internal, V1 to V2, T equals constant. What is delta S of the system? Okay, this is the expression for delta S of the system, or ds of the system. Okay, so delta S of the system is the integral of dq reversible over T. The T is constant by its definition, so this is the reversible heat over temperature. Okay, let's assume it's an ideal gas. Ideal gas. Further on, we assume it's an ideal gas. So what is delta U? Delta U is 0. Said last time the entropy, the internal energy of an ideal gas depends only on temperature. We said that last time, not on P and V, because the molecules aren't reacting with each other. Delta U is 0, so that's equal to W reversible plus Q reversible. So therefore Q reversible equals minus W reversible. So delta S is equal to minus W reversible, minus the reversible work over T. Okay. And on last Thursday, I worked out the reversible work of expansion of an ideal gas isothermally with RT log V2 over V1. Okay, remember we did that last time, the Gibbs Energy, the work, it's in your notes from Thursday, the work of expansion of an ideal gas from V1 to V2 isothermally, etc., is nRT log V2 over V1. So putting that in here, I end up with delta S equals, and make sure I don't make a mistake, nRT log V final over V initial divided by T, and the T's cancel. Okay, so delta S then is nR log V2 over V1. So that is the entropy change for expanding the ideal gas. And we have, this is important, the actual process is not reversible. I'm saying the gas is expanding irreversibly against an external pressure which is not equal to which is less than the internal pressure. So it's a spontaneous process. It's not equilibrium, it just goes. Okay? It's not, the process is not reversible. But we calculate the entropy for a hypothetical reversible path between the same initial and final state. To calculate the entropy, you take a hypothetical reversible path from the initial to the same final state. It's the same initial and final state. The initial state was P1, V1, the final state was P2, V2 at the same T. I'm saying I go reversibly between those two paths. So reversibly, I don't have a constant of P external. I put my hand on the piston, I let the external pressure equal the internal pressure, and I very slowly let it expand. That is my hypothetical path, and that is how I calculate delta S. Delta S now is positive because V2 is greater than V1. Okay, does this go along with your idea of entropy being disordered? Well, when the volume is smaller, then the gas molecules are constrained to a small space. As the volume gets bigger, they got more room to move around. They're in bigger space, they're less ordered, they're less localized. Being less localized, it's more disordered. Okay, so the delta S is positive. That's the delta S of the system, and it was calculated for a hypothetical reversible path between the same initial and final condition. Now, what is the total entropy of the system? The total entropy of the system takes into account the energy change of the surroundings as well, the entropy change of the surroundings. So I'm running out of board here, so what I'm going to do is put this piece of paper over this. Cut this out. Delta S of the surroundings equals, well, if delta S of the system is dq reversible over the T, delta surroundings is q of the surroundings over T. You consider now the surroundings is like the system, so the entropy change of the surroundings is q of the surroundings over T. Q of the surroundings is minus q system over T. The heat absorbed by the surroundings is the heat lost by the system. Okay, so what is the heat of the system? Del du is Q plus W. Okay, it's equal to Q reversible plus W reversible, but for an irreversible process, it's equal to Q irreversible plus W irreversible. Whatever the process is, del du is Q plus W. Okay, W and del du is still 0. Doesn't matter if it's reversible or irreversible, you're still going from an ideal gas at T to an ideal gas at the same T. So del du is still 0. Okay. What's W irreversible? W irreversible is simply equal to minus P external delta V. That's the work the system does is minus P dV, minus P delta V. But it's the actual work is minus P external delta V. As I said yesterday, if there's no external pressure, there's no work done. So it's minus P external delta V. And so since Q plus W, Q irreversible is P external delta V. So if the system is doing, basically you're keeping the temperature the same, so you're doing work, you have to add heat to the system to keep the temperature constant. Talked about that on Thursday. Okay, the system is doing negative work here, so if there were no heat added, the system would cool down as it lost energy doing the work, so you got to add heat to it. Okay, so Q irreversible is P external delta V. So if you take this thing here, that's the surroundings. So therefore delta S of the surroundings is equal to minus P external delta V. Okay. So what? No, what? Oh, sorry, yeah, minus P external divided by 2. You're unhappy with it. So that's the entropy change of the surroundings. So the entropy change of the system will be positive. The entropy change of the surroundings is negative. If the entropy change of the surroundings equals the entropy change of the system, that is, if I organize things so that the external pressure is always equal to the internal pressure, the total entropy will be 0 and the system's at equilibrium. If suppose the external pressure was very low, in that case the entropy change of the surroundings would be only slightly negative. The total entropy change then this plus this, so we'd have delta S total. Delta S total is nR log V2 over V1 minus P external delta V over T. This is a positive term. This whole thing comes out to be negative. Okay, it's the balance between the two that is important. Okay. If the two are equal, that is, if the external pressure is always equal to the internal pressure, the two are going to be equal and the delta S total is 0. If P external is very small, then the negative term is small, the positive term is large, delta S total is positive, and the expansion is spontaneous. If the P external is very large, okay, this term here will be more negative than this term, which simply means that delta S total is negative, which means that the reaction in the other direction will be spontaneous. If P external is greater, that is very large, greater than P, the spontaneous direction is compression. Okay, in this case, the spontaneous direction is direction. Another way of looking at this, then, is simply that this first term is Q reversible over T. The second term is minus Q irreversible over T. Okay, or that's equal to minus W reversible over T plus W irreversible over T, whichever way you want to look at it. Okay. The first term, the entropy term for the system is the reversible heat over T. The entropy term for the surroundings is the irreversible heat over T. Or the other way, the first term is the reversible work, the second term is the irreversible work. Remember that we're talking about an expansion here, and I showed you the other day we had the PV thing, and I said, let's say we're going, this is the pressure of the system. Okay, so the reversible work is the integral of P dV. Reversible work is the area under the curve. If you had a P external, so this is P internal, say you had a constant P external, and now you're expanding against a constant external pressure, in that case the irreversible work is this area here, which always must be less than the reversible algebraic, at least in absolute terms. The reversible work that the system does is the area under this curve, P dV. Okay, the irreversible work is P external dV, which is always less than P dV, or algebraically it's more negative. So this term, this minus this, is always going to be positive. It's the difference between the reversible and the irreversible heat. The reversible work is always the maximum work what the system can do.
What would be if the pressure, external pressure, is higher than the final
If it's higher, then the irreversible work would be greater than, the irreversible work would be greater than, but going in the other direction.
And how would you calculate the...
It's still P external dV, but P external would be, say, up here. So it's a difference. So really, the delta S of the system is actually telling you how far you are from reversible conditions, which are equilibrium conditions. So the delta S is a measure of the distance away you are from equilibrium. If you're at equilibrium, if the external and internal conditions are the same, then the system's at equilibrium and delta S is 0. It's the difference, Q reversible minus Q reversible over T tells you how far away. The further you get away from equilibrium, that is, the lower the total pressure or the higher the total pressure. Okay, so delta S total then is a measure of the driving force for the reaction. It tells you how far you've deviated from the equilibrium condition. Okay, but the important point is the entropy, well, one important point is the entropy of the system has nothing to do with the external. Once you have the initial condition and the final condition, you can calculate the entropy of the system by finding a hypothetical reversible path. If you could find another hypothetical reversible path and do the calculation, you'd get exactly the same entropy. This is the simplest way of doing it. Okay, but you get the same entropy. But the entropy change, now to answer your question then from a few minutes ago, the entropy change of the system over T, which is the delta S of the system, is independent of the path, because it's just S final minus S initial, because S is a state property. But the Q surroundings over T depends on the path. In other words, it depends on the external pressure. Okay, so in a very different, between the same initial state and the same final state, you can have many different external pressures. So it's the entropy change of the surroundings that changes. And it's going to be the same in chemical reactions or anything. This is just one example. But in any system, any change of state, the entropy change, if you have an initial and a final conditions, the entropy change of the system is independent of the path. It's just S final minus S initial. The entropy change of the surroundings is what tells you whether you're on one side of equilibrium or on the other side. And delta S then, in a sense, is more than in a sense, it is the driving force for the reaction.
To calculate the delta S of surrounding, you make an assumption that you consider the surrounding as a system or
Yeah, it's a heat sink. It's a heat sink at the same temperature as the system. Nothing happens, there are no irreversible processes in the surroundings. The surroundings are simply a shell around the system. No irreversible, you define your system so that anything irreversible, like a chemical reaction or whatever, is going on in the system. The surroundings are at the same temperature, and they simply see a transfer of heat at constant temperature. Now you'd say, well, let's say the surroundings are at a different temperature. The real surroundings are at a different temperature. Okay, in that case you have to consider a separate process. You would have the system, here's your system. Okay, in the purposes of what we're doing, you would have a shell around, you consider this to be this is a T, T1, and the surroundings are at the same T1. The process we're considering is the things going on between the system and what's going on in the system and the surroundings here. Now, if here you had another T2 out here, then you're going to have a heat flow from the surroundings to T2, but that's a separate process. Okay, we're only considering the process going on in the system, and in that case we're considering the transfer to the surroundings at the same temperature as the system, in which nothing happens but a transfer of heat. If anything else goes on out here outside the system that's irreversible, then that's a separate process. The transfer of heat from T1 to T2 is an irreversible process, and that's a separate irreversible. So you'd have to consider that to be a separate process. Now the entropy, if you want to consider the global overall thing, you put the two processes together, and the total entropy change would have to be positive for the universe. We're trying to separate out the various irreversible processes. So we're considering the irreversible processes concerned with the system and the surroundings. If there are other irreversible processes like a transfer of heat to a different temperature in the real surroundings, well then that's a separate process. We treat them separately and then add them up after. There's another way of presenting thermodynamics, which many people prefer, in which you consider a closed system, but you don't, the surroundings, you don't, it's a an isolated system, adiabatic. And so this heat the heat of the system, the irreversible heat goes to heat up the system. So the system, rather than transferring it out at constant temperature, you produce heat which actually heats the system up and changes its entropy. I find this a really confusing way to present the thing. I like it this way. You'll see it the other way as well. I find that's kind of gets things really confused, because then you got different entropy effects, which are kind of hard really to separate. You have the irreversible entropy effect and you have the heating effect. I'd rather see the heating effect in the surroundings rather than taking part in the system, because it's just too complicated. That's the way I look at it. Well, then let us continue on with this idea about the initial and final state being the same, hypothetical paths. Let us suppose that we have, now we're going to have a gas, I just do that actually. Say a gas expands into a vacuum, it's going to be the same thing. We have 1 mole of oxygen. And here we have a vacuum. And what we do is we allow the 1 mole of oxygen to expand into the vacuum. That's the process. So the initial state is 1 mole of oxygen in the vacuum. In the final state, we open the thing, we have a 1/2 mole of oxygen here and a 1/2 mole. And T is constant. All right. What is the entropy change for that? Clearly it's positive. T is constant. This is an ideal gas. There'll be no heat effect. There's no work connected. The ideal gas, the molecules don't see each other, so there's no change in internal energy of the system, so there'll be no change in temperature of the system. You could insulate it from the surroundings. It doesn't matter. There's not going to be any exchange with the surroundings. Now clearly entropy change should be positive, because it's obviously a spontaneous process, and it's an irreversible process. You open the valve and it goes woof, so it's irreversible. So in order to calculate the entropy change, we must calculate the entropy change for a hypothetical reversible path. Okay, and that is simply then we have 1 mole of oxygen expanding reversibly to twice the volume. And we already did that. We have delta S is m r log v2 over v1. We just did it for a reversible path. So the reversible path is you put a piston here, you hold your hand, you let the thing slowly expand. Okay? That's a hypothetical reversible path between the same initial and final conditions. The actual process is not reversible, but you calculate entropy for a hypothetical reversible path. And so this is n r log of 2. And it's positive. And in this case, the entropy change of the surroundings is 0. Everything's occurring in the system. Okay, chemical change or entropy change of chemical reactions. Okay, so I consider the reaction lead solid plus 1/2 mole of oxygen gas gives PbO solid, and we'll put this at 298, and we'll put this at 298, and pressure is 1 bar. Okay, and I'm trying to calculate whether this is a spontaneous reaction or not. Now for this reaction, this is what I defined out, and I look through my thermodynamic tables, and I find a delta H for the reaction. Or I could find absolute enthalpies for each thing, but I mean we know that the absolute enthalpies of this and this are 0 by convention, so it comes out the same thing. The enthalpy of reaction, which could have been measured in a bomb calorimeter, is minus 218,062 joules, which is less than 0. So it's an exothermic reaction, heat is given off. I also look up in my tables and I want to calculate delta S. And what I see in my tables, I do not see 0, 2, because this is all standard state, pure PB, pure PBO, oxygen to 1 atmosphere. Delta S, I look up delta S and I find tables that don't give me delta S because S is an absolute quantity. And I actually find in my thermodynamic tables I have absolute values of S. So delta S is going to be, delta S0 would be the standard entropy of PBO minus the standard entropy of lead minus 1/2 the standard molar enthalpy of oxygen gas. Okay, entropy of the products minus the entropy of the reactants. And I look this up in my tables, and I find, or I use ThermFact FactSage, and I see that this is 68.7 joules per mole. This is equal to 64.8 joules per mole, and this is minus 1/2, 205.1 joules per mole. First of all, I notice a couple of things. I notice that the entropy of PB and PBO are more or less the same. They're both solids. And I notice that the entropy of oxygen, however, is much greater than the entropy of PB and PBO because it's a gas. And a gas is more disordered than solids and liquids. It's going to have a higher entropy. So what's happening here is we're going from a solid plus a gas to a solid. So the gas is reacting with the lead and lining up to form a nice crystal lattice with PBO. So you can see clearly from this that delta S for this process is going to be positive. Sorry, no, this is going to be negative. What am I doing? Sorry, yeah, delta. Delta S is negative. So delta S is negative for the system, and I actually worked it out. Minus 98.7. Okay, as you would expect, delta S will be negative because the system is becoming more ordered, because you're replacing a gas by a solid. All right, okay, so we know this is a spontaneous process. You know that if you leave lead out in the air, it may take a little while, but the lead will oxidize spontaneously. If you leave lead, no matter what the temperature is, in an oxygen gas of 1 atmosphere, it's going to oxidize spontaneously. Okay, so it's a spontaneous oxidation, yet the entropy change is negative. Okay, so what's the problem? The problem is it's not the entropy change of the system that counts, it's the total entropy change, system plus surroundings. So the system is becoming more ordered. Nevertheless, it's an exothermic reaction, so it's giving off heat. It heats up the surroundings. The surroundings have an increase in their entropy. Just like the example I gave you before with the fusion, the melting, below or above the melting point. So, what is delta S of the surroundings? Delta S of the surroundings is Q of the surroundings divided by T, because again, the surroundings is, I think maybe I didn't answer your question there right earlier. The surroundings is this heat sink. All the surrounding sees is a transfer of heat at constant temperature, which is always a reversible process. Okay, so delta S surroundings is Q reversible of the surroundings. Okay, but all the surroundings ever sees is a transfer of heat at constant temperature, so that's a reversible process. You have two things that equal at same temperature, transferring heat at constant temperature is reversible. It's at equilibrium. So we can remove the reversible. This is just Q surroundings over T. And Q surroundings is minus Q of the system over T. And the Q of the system, since it's at constant pressure, is minus delta H over T, and so that is plus 218,062 over T. T is 298.15. Let's say T is 298.15, and that gives you 731.4. Okay, so the entropy change of the surroundings is very positive because it sees a large amount of heat going into it. And the total entropy change then, which is delta S of the system plus delta S of the surroundings, is very positive. So it's a spontaneous process. Okay, Gibbs Energy. Okay, so far we've talked about the entropy change as total entropy change, system plus surroundings, is the criterion. That's the general criterion for any process. Any process under any conditions, del S will be positive if it's a spontaneous process. Del S will be negative if it's an impossible process, or spontaneous the other way around. Del S total 0, it's at equilibrium. It's a bit inconvenient, however, to always be talking about the surroundings. We would like to do everything in terms of the system. Okay, well you can see right here, we're talking about Q of the surroundings, but Q surroundings equals minus Q of the system, which is minus delta H. Now remember, the heat at delta H is the heat under certain conditions at constant temperature and constant pressure, but that's what we have here. We have a constant temperature and a constant pressure, and these are very common conditions. Okay, so if you do the whole thing, the delta S total then, delta S total is delta S system. In general, we don't have to put the subscript system. If there's no subscript, we're talking about system. Okay, plus delta S surroundings. And now we have temperature and pressure are constant. So that's equal to delta S, and now the delta S surroundings is equal to minus delta H over T. Delta S of the surroundings is Q surroundings over T, which is minus Q system over T by the first law. If T and P are constant, Q system is delta H. Okay, so delta S total is delta S minus delta H over T, provided that we keep the temperature and pressure constant. Okay, so delta S and delta H are properties of the system. Okay, so now we have it in maybe a little simpler form. Okay, so delta S total, if the temperature and pressure are constant, special case, is equal to the entropy of the system minus delta H over T. It's the total entropy. Is everybody? Okay, so now I'm going to make a new definition. I'm going to find a new property of state called G, which is called the Gibbs energy. It's also called in English the free energy. Free enthalpy would probably be a better term. In French it's the enthalpie libre, the free enthalpy. But to get around all those problems, I call it the Gibbs energy. And H, T, and S are properties of state, so G is a property of state. Delta G is independent of the path, of course. Okay, but now we clearly see what happens if I take delta G is equal to delta G at constant T and P is equal to delta H minus T delta S. Okay, and if you look down here at constant T and P, that's equal to minus T delta S total, which is going to always be negative or equal to 0. Okay, so for this is a special case of the second law. The general case of the second law is that the delta S total must be positive. But under conditions of T and P being constant, delta G at constant T and P is delta H minus T delta S, which is equal to minus T delta S total, which is negative. Okay, so this is a special case of the second law. Delta G at constant temperature and pressure, which is equal to delta H minus T delta S, is less than or equal to 0. Less than 0, it's a spontaneous process. Equal to 0, it's at equilibrium. Greater than 0, it's spontaneous the other way around, or impossible in the direction as written. Okay, now we do this for convenience because it puts everything in terms of properties of the system in cases which are very common, constant T and P. Okay, so negative Gibbs energy is nothing but a special case of the second law, but a very important special case of the second law. So I derive that whole thing here, and we end up with dG at constant temperature, pressure, and a closed system, by the way. So dG at constant Tp and constant number of moles is equal to minus TdS total. This is a special form of the second law for a process occurring in a closed system at constant T and P. So such a process will be spontaneous if dG is negative. And this is the most useful form of the second law. Your question that you asked about, it might be raised that this only applies when the surroundings are at the same temperature of the system. However, you consider that the surroundings at a different temperature, we postulate a hypothetical heat reservoir at the same temperature of the system, etc., which I already went through. You could also show that dg, well, we did this before in terms of S, but dg is equal to the dq, which is the actual heat of the system, minus the reversible heat of the system. And that's got to be less than 0, or equal to 0. If the system is reversible, dq is equal to dq reversible, that's equal to 0, and the system's at equilibrium. If dq is greater than q reversible, then it's positive, and the system is, and so on. Okay, so again, it's the deviation from, it's how far away the system is from, oh, sorry, I don't have the damn thing on it. What happened with it? Why do we not have a...
No light? No light?
Right. Doesn't do it. Anyway, it's time for a break. I'll take a 10-minute break. I'll just do a few minutes after the break. But during the break, let's try to fix this thing.
Okay.
So, you wanna... How long has that been off? Sometime? Starting to 12. Go.